Hello Vulkan developers! In the previous video we learned how to use the specialization constants, which allow you to create multiple variants of the same shader optimized for a specific set of variables. These variables are provided during the creation of the graphics pipeline object. Now, I've also mentioned two other methods for passing data into shader variables: uniform buffer objects, or UBOs, that we are already familiar with, and push constants. Today we will take a look at the latter. Those of you who have some experience with Vulkan are maybe asking yourself, why did it take 30 tutorials to reach this topic? Well, the reason is that most of the benefit of push constants is when we record the command buffers on every frame. However, in this series I made an effort to prepare all the command buffers that we will need offline before the main render loop begins. This may change in the future, but that's how the codebase works right now. But I still want to cover push constants because they are important, so I had to come up with some use case for them in the current setup. Here goes. Push constants are one of the fastest ways to send data from the CPU down to the shaders on the GPU. While UBOs are great for large chunks of data, they come with the overhead of memory allocation and descriptor sets. Push constants, on the other hand, live directly within the command buffer. This makes them perfect for high-frequency updates, like transformation matrices that usually change very often. Once the command buffer has been recorded with some push constant values, it cannot be changed. So if you want an efficient method for accessing a highly dynamic variable such as the WVP matrix, you can store it in a push constant. But then you have to record the command buffer on every frame. Well, we can't do that in the current setup, so we need to do something else. Enter the BigTextureArray. That's an array of textures that holds all the materials across all the assets in your game. In our existing descriptor layout, we have a single set with multiple resources: vertex and index buffers, a texture, a couple of uniform buffers, and a metadata buffer. To use the BigTextureArray, we will separate this layout into two sets. The first set will be dedicated to the texture array. The system will create a single pair of descriptor layout and set, and will populate the descriptor set with all the materials in the application, one block of materials after the other, across all assets. In every draw call, this descriptor set will always be present on slot number 0. The second set will include the other resources, vertex and index buffers, and etc., which may change between models. Before recording a draw command, we will bind the two sets together, the BigTextureArray on the first slot and the specific descriptor set of the asset on the second slot. Now there is a problem, of course. How would the Fragment shader know where to access the array of textures? Each model is familiar only with its own materials. It doesn't know anything about the arrangement inside the texture array. This is where push constants can be useful. We will use a push constant to store the base texture location for each model. In the Fragment shader, we will add the material index to the base texture location, and this will give us the final index into the array. This type of information about the BigTextureArray is constant throughout the execution of the program, so it is safe to record it into the command buffer once and reuse it multiple times. Let's go over the required changes, bottom to top, starting from the Fragment shader. We define a GLSL structure of a uniform type called constants. This is the name of the structure, so it can be anything. The structure contains a single unsigned integer called base texture index. We instantiate the structure using the variable name push. This, of course, can also be anything. To make it a push constant, we specify the layout as push_constant. To use it, we simply write push.baseTextureIndex. We add it to the existing material index and access the texture array. By the way, notice that the texture array is specified with square brackets and without a size. This requires the use of descriptor indexing, which is the focus of tutorial 26, so make sure to watch it. Descriptor indexing is often used to enable big texture arrays, so I consider it to be a baseline for this tutorial. Also notice that the texture array is on binding point 0 on set number 0. The uniform buffer moved to set number 1, binding point number 4. In the Vertex shader, we can see that all the resources are also on set number 1, binding points 0, 1, 2, and 3. Okay, same resources on two different sets instead of one. This completes the changes on the shader side, so let's take a look at the application. To consolidate the management of the big texture array, I created a new class with the proper name. The class maintains a Vulkan device handle, a descriptor set layout, a vector of descriptor sets, we need one set per swap chain image, and the binding point. This is 0 in this demo, but can be configured to be anything. The creation of the texture array is a two-step process. First, we initialize the class by calling init. This can be done as soon as we have a device and a descriptor pool. We also need to specify the number of swap chain images, the maximum number of textures we plan to support, and the binding point. Later on, once all the assets have been loaded, we call createTextureArray with the vector of the model desk structure. This structure contains the information about all the resources maintained by the vkModel class, and you should be familiar with it from previous tutorials. This function populates the descriptor set. The init function is very simple, so I will just mention the important stuff. First, we create the descriptor layout, and then we allocate the descriptor set. To create the layout, we specify the layout create info. This guy points to a single layout binding structure. The key things here are the binding point, the descriptor count, which is the maximum number of textures, and the shader stage, which is the fragment shader in our case. Now, to make the big texture array actually work, we need a secret sauce, which is the following binding flags. Partially bound. Usually, every single slot in a descriptor array must point to a valid vkImageView. If you have a 1000 slot array, but only load 50 textures, Vulkan will crash or throw a validation error when you bind it. This flag tells Vulkan that it's okay if some slots are empty. Variable descriptor count bit. Standard layouts have a fixed size baked into the pipeline object. To change the array size, you'd have to destroy and recreate the entire pipeline. This flag allows the actual size of the array to be decided at descriptor set allocation time instead of the layout time. So you can create a new descriptor set with a different size using the same layout. And finally, update after bind bit. Usually, once we record CMD bind descriptor sets into a command buffer, that descriptor set is locked. You cannot change its textures until the GPU is completely finished with that buffer. This flag unlocks the set. You can call update descriptor sets to swap a texture even after the command buffer has been recorded or submitted. Now, some of these flags may seem unnecessary for today's demo, but I want you to be familiar with them to allow you to create more flexible engines in the future. To use the flags, we have to create a descriptor set layout binding flags create info. The binding count must match what we have in the layout create info, and p binding flags must point to the binding flags. The address of this structure must be set into the pnext pointer of the layout create info. Oh, and don't forget that to make the usage of these flags even possible, we have to enable a few feature flags when creating the logical device. So remember that we have previously created an instance of the physical device Vulkan 12 features, which is pointed to by the pNext pointer in the device create info structure. We've already enabled some stuff here, so now we have to add the descriptor binding partially bound, which matches the binding partially bound bit, the descriptor binding variable descriptor count, which enables the bit with the same name, and descriptor binding sampled image update after bind, which enables the create update after bind bit. Next we have the allocation of the descriptor set. This is pretty standard, so I just want to point out that because of the variable descriptor count bit flag, we have to specify the descriptor set variable descriptor count allocate info structure. It points to an array of unsigned integers. The size of the array matches the number of descriptor sets, which is the number of images, and the value in every element is the maximum number of textures. This structure is pointed to by the pNext pointer of the allocation info structure. Finally, we have the function that creates the texture array. This function takes a vector of the model desk structure. It goes over the vector and counts the total number of textures. Next, it prepares a vector of descriptor image info structures and resizes it to this value. We can now traverse the model desk vector again and initialize the descriptor image infos. Basically, the materials of each model desk are concatenated one model after the other. Notice how the index in the destination array is always incremented after each element. Now that the image info array is ready, we can populate the right descriptor set vector as usual. For each descriptor set, we have a single element. We set the binding point. The descriptor count is the total number of textures, and we have to set pImageInfo to point to the image info array. The BigTextureArray is now ready for prime time. To start using it, we have to make a few changes to the LightingProgram class. This class was introduced in the previous tutorial, and it is stored in the actual tutorial directory and not in the Vulkan core project. This makes it easier to make changes to it from one tutorial to the next. First, I had to change the interface of the function createDeskSetLayout. This is a virtual function which is defined in the base class, and every program class must implement it in order to specify its own unique layout. Previously, this function simply returned the layout handle. Now it returns a vector of handles. This allows us to support multiple sets. This function creates the same binding points, minus the texture, and returns a vector of layout handles with two elements. The first one is for the textures. This guy is a new private attribute which is set by the layout from the BigTextureArray class. The second layout is the one that was created locally here. Next, we have some changes in the function that binds the program to the command buffer. In a similar fashion to the layouts, the bind function in the base class was expanded to receive a vector of descriptor sets. The first one is again the set from the BigTextureArray class, and the second is the parameter of the function and belongs to the current mesh that we want to render. We call the bind function in the base class, which in turn calls cmdBindPipeline and cmdBind descriptor sets. This function knows how to handle an array of sets, so this works well with our interface change. Back to the previous function, we have a new call to cmdPushConstants. This function actually bakes the values of the push constants into the command buffer. We specify the pipeline layout, the shader stage, the offset inside the push constant block, the size of the data, and its address. As you can see, this function takes the base texture index as a parameter. This means that the application must maintain the base index for each model, but as we saw with the BigTextureArray, this is very simple to do. At this point, we can run the program and most likely it would work, but in the console we can see the following messages from the validation layers, which basically tell us that push constants were used without specifying their size in the pipeline layout. This object is created in the function createPipeline of the base class graphics pipeline. To make this function support push constants, I've added a virtual function getPushConstantRange, which returns a vector of vkPushConstantRange structures. The default implementation returns an empty vector. If the vector is not empty, we set the pushConstantRange count to the size of the vector and the pushConstantRange's pointer to its base address. This function is implemented in the LightingProgram class. The vector contains a single element with the following attributes. The stage is the fragment shader, the offset is 0, and the size of the push constant is the size of an unsigned integer. Make sure these properties match what you have in the shader. We can finally see it in action. In this demo, I'm rendering several models, each with its own materials. As you can see, the models are rendered with the correct textures. And that's it for today. If you found this video to be useful, please hit the like button and subscribe. Thank you for watching, and I will see you next time.